lecture. Right, thank you. So I've spoken about this material a number of times, and very often I've had the experience that there is a number theorist in the audience, and the number theorist at the end says something like, "That was great, but could you say it with more L functions?" And that's not really a language that comes naturally to me, so my answer is always, probably, but I wouldn't know what to say off the top of my head. But when I was preparing the notes for this winter school, I realized I was going to be talking to an audience consisting entirely of number theorists. So I should probably figure out how to say some of what I wanted to say using L functions. So that's what I'm going to do in this lecture, but with the caveat that the L functions are actually irrelevant. The only thing that I'm actually going to do with L functions is evaluate them at s equals 0. But nevertheless. So maybe this audience doesn't consist entirely of number theorists, so let me start just by reviewing a little bit about what L functions are. So my setting X is going to be an algebraic variety defined over a finite field, FQ. What's that? It's blurry. Oh. What about this one? Oh, sorry, it was a technical issue. Okay. All right, so let me remind you that if you have an algebraic variety defined over FQ, you can associate to it a function called its zeta function. Zeta x, it's a function of a variable s, and what it is, it assigns to s the product over all the closed points of your variety, 1 over 1 minus the size of the residue field at that point, raised to the power minus s. So this is some generating function which contains information about the number of points that your variety has with values in various finite fields. It contains the same information as the number of points that X has with values in FQ, FQ squared, FQ cubed, and so forth, and it packages this information in a useful way. So, and it's called the zeta function of X because you can write down more or less the same definition where X, instead of being an algebraic variety over FQ, is instead the spectrum of Z, and in that case, this would be the Riemann zeta function. Okay, so the zeta function of a variety over a finite field is a much simpler object than the classical Riemann zeta function. It's actually something that you can write as a rational function in q to the minus s. So this maybe is definition 1, which is very concrete. Definition 2, slightly less concrete, is that zeta x of s is something that I'll write, well, it's a product over I greater than or equal to 0 of the determinant of 1 minus the Frobenius times q to the minus s on the ith cohomology of x, and it's some kind of alternating product. So this alternating products like this are going to appear a lot in this lecture, so I'm just going to give a name to this alternating product. I'm going to call this the determinant of 1 minus phi times q to the minus s on the cohomology of x with an inverse sign. So the equivalence of these two definitions is a form of the Grothendieck-Lefschetz trace formula that I mentioned earlier. Okay, so this is the zeta function of a variety. I want to talk about a generalization of this, which is like a zeta function with coefficients. So now let f be an L-adic sheaf. On the variety x. So let me introduce some notation that I'm going to use when talking about L-adic sheaves. So if I have a point, a closed point of my variety, I can think of it as giving me a map from the spectrum of a field into that variety, namely the residue field at that closed point. And I would like to refine that to a geometric point of my variety by choosing an algebraic closure of that finite field. And this composite map is something that I'll denote by x with a bar over it. So that's just a geometric point lying over the actual point x of the underlying topological space. So then if f is an L-adic sheaf, I can talk about its stalk at the point x with the overline here, and this is just going to be a finite dimensional QL vector space. But because it comes to me, so this QL vector space, you can think it's obtained by taking my sheaf f, which lives on x, first restricting it to the point x without the overline. That gives me an L-adic sheaf on the spectrum of a finite field, and then restricting it to the spectrum of the algebraic closure of that finite field. At the intermediate stage, we see that we get some information, which is that this QL vector space has a canonical automorphism called the Frobenius map. And, well, it's the Frobenius map associated to the finite field kappa x. So I'm going to denote it by phi sub x. So this is some QL linear map. And now, so definition. One of the L function that's associated to this sheaf, I'll write it as L of f comma s. Again, this is a function of s being a complex number, and it's something that I can write as product over all the closed points of my variety of now the determinant of 1 minus the size of kappa x raised to the power s times the Frobenius x on this fx bar with an inverse there. So this is definition. Oh, maybe I should emphasize when I write that this is the definition. This is the definition provided that the real part of S is sufficiently large, which guarantees that this infinite product converges. And you can define it for almost all values of S. Then by analytically continuing, I mentioned earlier that in the case of the zeta function, this turns out to be a rational function of q to the minus s, and the same thing is true for this L function, because this is equivalent, again, by the Grothendieck-Lefschetz trace formula, to another definition. Let's call it definition 2. The L function of f evaluated at the point s is something that you can write as a product of, using my earlier convention, it's the determinant of 1 minus the Frobenius. Now that's the Frobenius on associated to fq, q to the minus s, on the compactly supported cohomology of x bar. But now you don't take cohomology with constant coefficients, you take cohomology with coefficients in this sheaf F. And so remember, this determinant really means an alternating product. So this is defined as the product over I greater than or equal to 0 of some determinant on hi raised to the power minus 1 to the I plus 1. Okay, so this is just a relative version of the zeta function. If you specialize to the case where f is the constant sheaf, just QL everywhere, then it recovers the zeta function of the variety x. Okay, I'm going to need a slight generalization of this. I want to talk not about a single L-adic sheaf, but a complex of L-adic sheaves. So let dB of x be the bounded derived category of QL sheaves. So I'm going to use the letter F to denote a typical element of this bounded derived category. So it's roughly speaking, you can think of these as chain complexes of L-adic sheaves, although that's not quite right. But these objects of this category have the property that you can associate to them. So for each integer I, you can associate what I'll write as, that's supposed to be a script h, the ith cohomology of f, but in the world of sheaves. So this is going to be an L-adic sheaf on x in the sense of the previous slide over there. And now this symbol B indicates that I want to consider the bounded derived category, meaning that these cohomology sheaves, these vanish for almost all I. Okay, and now given an object in this bounded derived category, you can also associate an L function. And you just do something stupid. So definition, here's what I mean by the L function of x with coefficients in f. Now where f is in the derived category, it's just an alternating product of the L functions of the cohomology sheaves of f. So that's a definition, and well, again, there are two versions. Let me just write them out so that we have them for later. Depending on whether I take definition 1 or definition 2 as my definition of the L function of an L-adic sheaf, I get two different descriptions of what I mean by the L function of a complex. So definition 1 is that the L function of f at the point S is a product over, closed points of my variety and integers I of determinant of 1 minus the size of the residue field. Sorry, I just realized this isn't going to be big enough. Phi sub x restricted to, what I should put in there is the stalk of hi of f taken at a geometric point lying over x. So that's the sort of concrete definition that doesn't require thinking about cohomology. So that's version 1, but it's also something that we can write by thinking not about the stalks of this sheaf, but instead about the cohomology of that sheaf. So L of f comma s can also be written as, let's call it the determinant of 1 minus the Frobenius times q to the minus s on, I'll again write it as h star of x with coefficients in f. But now this f is a complex now, so when I talk about the cohomology, it's what's sometimes called the hypercohomology. Of x bar with coefficients in f. And again, the equivalence of these two definitions follows from the Grothendieck-Lefschetz trace formula. Okay, so I would like to cook up an L function that is relevant to the situation that I've been talking about in this series of lectures. So I'm actually going to describe, well, I'm going to assert the existence of certain objects which are relevant to the story. So, claim. So, I won't make the claim yet. So first, some setup. So let X be a variety. Actually, well, let me start by just recalling something that we said in the previous lecture. So recall. So if Y is a variety or a stack defined over a finite field K, and in the previous lecture, I made some assumptions about the Y that I was interested in. I assumed that H1 of Y bar with Z mod L coefficients was 0, and that HI of Y bar with Z mod L coefficients is finite for all I. And, well, I should probably say this for H0 also vanishes. So Y is, I said it was a variety. Well, I'll emphasize it by saying it's geometrically connected. So under these assumptions, in the previous lecture, I talked about assigning to Y bar what's called its L-adic homotopy type, and in particular, its L-adic homotopy groups. So then we have L-adic homotopy groups, which in the previous lecture I denoted by pi n of Y bar with QL coefficients. So these are finite dimensional vector spaces over QL, and moreover, since they're defined just in terms of Y bar, but if I know Y bar comes from some Y, which is defined over a finite field, then these finite dimensional vector spaces have a canonical automorphism coming from the Frobenius of the ground field. So let's just say with a Frobenius. So this is the story that I told in the previous lecture, and what I would like to do now is a relative version of this. I want to think about this not for a single variety Y, but I want to imagine that I have a family of Y's parametrized by some other variety X. So here's the relative version that I would like to contemplate. So X, as before, is going to be some variety over FQ. And this is ultimately going to be the algebraic curve from the second lecture. And now let Y be some, could be an algebraic variety, but more likely it's going to be an algebraic stack mapping to X. And I'm going to assume that this map is smooth. And now for each closed point of X, I'm going to write Y x bar to mean what you get when you take Y and cross it over X with that geometric point X bar that I mentioned earlier. So then this Y x bar is some smooth stack, which is defined over the algebraic closure of a finite field. And potentially, it's something that you could apply this story to. So now, in order for everything to work nicely, I need to make a lot of assumptions about how nice Y is. So I'm going to assume that each Y x bar, has vanishing H1 with ZL coefficients. I'm going to assume that it has finite HI with ZL coefficients. And moreover, I want to put myself in a situation where these L-adic homotopy groups live in finitely many degrees. And so I'll say also have vanishing pi n with QL coefficients for n sufficiently large. And that, moreover, I want to assume that this is true uniformly, meaning the n, I can choose my n so that it works for all the points x of my, my variety. So the claim is that, now I'll make the claim. The claim is that in this situation, I can define a relative version of these L-adic homotopy groups of Y. So that there exists an object, which I'm going to write as f sub y over x. And what sort of an object is this? Well, it's something that lives in this bounded derived category of L-adic sheaves on x with the following features. All right, so the main feature is that it is a relative version of these L-adic or homotopy groups in the following sense. So for each closed point of x, well, I can take, that's a script h, I can take the ith cohomology sheaf of f. So this is now an L-adic sheaf on my variety x. It's something where I can take the stalk at a geometric point, and when I take the stalk at a geometric point, I'm supposed to get a finite dimensional vector space over QL. And what I want is that for that to be the minus ith homotopy group of the fiber. And of course, I've said it in a way that maybe looks a little weird. This is not interesting if I is positive. This is interesting if I is negative. So the cohomology sheaves of F will be concentrated in negative degrees. Maybe I should write it like this. So this is for all I. So this is one feature that this construction should have. Another feature is that it is functorial. In Y, what I mean is that if I have some x and I have y mapping to x and some other y prime mapping to x, y prime mapping to y such that this diagram commutes, this gives a map from fy prime over x to fy over x in this bounded derived category of x. So this is supposed to be some a map which, when you pass to stalks and cohomology, it induces the map on homotopy groups given by the map from y prime into y. So I want to say that these sheaves fy over x, it's some global version of taking the L-adic homotopy groups of the stalks, and the functoriality is some global version of the fact that the L-adic homotopy groups are a functor of scheme Y. And I also want to say that it is functorial in X. In the following sense, so let's suppose that I have some y mapping to x satisfying these nice conditions, and I have some x prime mapping to x, and then I form the pullback. Y prime is y cross over x with x prime. Then in that case, so let me call this map from x prime to x little f. So in that case, what I want to say is that the sheaf that I'm going to assign to y prime over x prime, this lives in the bounded derived category of x prime. This should just be the pullback of the sheaf that I assign to y over x. And again, this is how things ought to work based on the first assertion that I've made, which is that these sheaves have the property that when you take their stalks, they're just computing the homotopy groups of the fibers. If you have a pullback diagram here, it means the fibers of this vertical map on the right are the same as the fibers of this vertical map on the left, and therefore they'll have the same L-adic homotopy groups. And I'm just saying that should be true not just on stalks, but globally. Okay, so I haven't defined for you these sheaves, but I'll say something about the definition at the end. But let's just believe for most of this lecture that there is a natural construction with the features that I've described. So I want to use it. So let's go back to our situation that we're really interested in, where x is an algebraic curve over fq. And now remember that when studying We's conjecture, we were interested in having a group scheme over x. So G is going to be a group scheme, which I'm going to assume is smooth, affine. The fibers are connected, and the generic fiber should be semi-simple and simply connected. This is just the setup that we had in Lecture 2, except in Lecture 2, I think I forgot to tell you the properties that I wanted my integral model to have. I wanted my integral model to have these properties. Anyway, given any linear algebraic group defined over the generic fiber, you can always find an integral model of it which has these properties that I've listed here. And if you started with a group over the generic point which was semi-simple and simply connected, then of course it will also satisfy this last condition. Okay, so in this situation, I would like to apply what I've been saying over here, but not to the map from G to X. Instead, I would like to take the classifying stack of G. So G is a group scheme over X. I can take its classifying stack that's taken in the world of algebraic stacks with a map to X. So to emphasize that this is an object that lives over X, I'm going to call it BG sub capital X. This is an object mapping to X. It's a stack, and it can be described as follows. If R is any ring, then maps from spec R into this object that I'm calling BG sub X should be the same data as maps from spec R into the curve X itself, plus a G bundle on spec R. And here, G is a group that lives over X, and therefore it makes sense to talk about a G bundle on spec R whenever spec R maps into X. Okay, so this BG sub X is an example of the kind of thing that I can take Y to be. What did I tell you I wanted to know about Y? I wanted to know that it was something with a smooth map to X that's satisfied by this BG sub X. I wanted to know that all of the geometric fibers looked like they were simply connected with simply connected with finite dimensional cohomology and finitely many homotopy groups. And in this case, the geometric fibers, as I asserted last time, they're classifying spaces of linear algebraic groups. Their cohomology rings look like polynomial rings on generators of even degree. So they're things for which the L-adic homotopy groups are very simple to have a simple description in terms of a tall cohomology. So we're in the setup. I'm about to run out of paper. So we're in the situation to which we can apply this construction that I asserted the existence of. So we get a sheaf, which I'm going to call F sub BG sub X over X. So this is something that lives in the derived category of X. And then to this sheaf, we can associate an L function. L F sub BG sub X over X. Coefficients in F, that's a little wordy, so why don't I come up with a notation for it? I'll just call it L sub BG sub X. S. Okay, so what can we say about this L function? Well, I would like to first just write down what its values are. So we have two formulas for how to evaluate an L function. So let me use the first of those formulas now. So by definition 1, what is this LBG sub x, comma s? It's given by the product over the closed points of x. I'm then supposed to take the determinant of 1 minus the size of kappa x to the power s, power minus s, times the Frobenius at the point x on the this sheaf BG sub x. Over x, I take its stalk at a geometric point, and then I put an inverse there. Okay, but we know what these stalks are, right? The defining property of this sheaf is that I know its stalks at geometric points should be computing the homotopy groups of the fiber. So this is a product over the points of x of the determinant of 1 minus kappa x to the minus s phi sub x evaluated on the determinant of that acting on the homotopy groups of the, well, let's call it BG sub x bar. And now, this was something that appeared in the previous lecture, at least in the special case where s is equal to 0. So let's put in s equals 0. L sub BG sub x comma 0 by Steinberg's formula. When s equals 0, we're just computing the determinant of 1 minus Frobenius on the the homotopy groups of the classifying stack of a linear algebraic group. And, well, by what we said before, this should be the number of points of BG with values in the residue field of x divided by the size of that residue field to the power dimension of BG, or, well, that's a little bit of a strange way to write it. A more concrete way of writing it is to say that it's the size of the residue field raised to the power equal to the dimension of G divided by the size of the finite group G of kappa x. Oh, sorry, and there's a product over all x and x. And you might recognize this product. It's one side of the mass formula. So what's the upshot? Sorry? Can I jump the page? Adjust. Like that? So what's LBG sub x at 0? Well, if I use definition 1 of L function, the one that's given by taking a product over stalks, this is equal to the right-hand side of the mass formula for appearing in We's conjecture for G. Now, as you might guess, we're going to try to get some mileage out of seeing what description 2 of this L function buys you. So description 2 says we shouldn't look at the stalks of this sheaf f bg sub x. We should instead try to think about the cohomology of this sheaf f bg sub x. And I want to relate that to the moduli stack of G bundles on x. So what's the relationship? So there's a relationship between this stack BG sub x, which lives over x, and this moduli stack bun GX, which lives over a point, spec FQ. So what is the relationship? Well, it's that if I take x cross bungx, there's a natural map to bgx, and this is all over x, right? What are the points of the left-hand side? To give an r-valued point of that product x cross bungx, I have to specify an r-valued point of the curve together with a g-bundle on x cross spec r. On the other hand, bg sub x, to give an r-valued point, I have to give an r-valued point of my curve together with a g-bundle, but not on the entire curve, just at that point. And so this is given by just restricting g-bundles to a point. So what does this buy me? Well, if you believe that the construction that I gave earlier is functorial in the ways that I said it was, it will connect something about bungee to something about bg. So this induces a map from, let's say, the sheaf that I want to associate to x cross bungx over x to this f of bgx relative to x. On the other hand, in this situation over here, I have a pullback square. Sorry, I was told not to do this, but I apologize to people on the internet. I have a pullback square which tells me how to describe this sheaf f x cross bungee relative to x. So let me call the projection map, let f be the projection map from x to a point. This is the pullback of just f of bungee x relative to fq. Okay, so there's this map from a pullback of a sheaf that lives on spec fq to this sheaf on x that is the one that I'm actually interested in. And let me just think of that a different way. Let me think of it not as a map from a pullback to something, but as a map from something to a push forward. So this is the same thing as giving a map, now in the world of sheaves on spec fq, from the one that I'm going to associate to bungee x to, well, I'm pushing forward in the derived category, so I'll write that as rf lower star of f sub bgx relative to x. And now, here's the theorem. Joint work with Dennis Gates-Gorey. Let's call this map something. Let's call it theta. Theta is an isomorphism. So this is a sort of local to global principle that describes the L-adic homotopy type of bungee x. And it's one way of making precise this heuristic idea that the cohomology of bungee x should be a continuous tensor product of the cohomologies of the bg at various points. So I'll elaborate on that a little bit more in the next lecture. But let's just see what it buys us. So assume this. Well, I'm saying that something is an isomorphism in the derived category, and it's the derived category of L-adic sheaves just on a point. So that's really just a concrete statement about, you could think of these, that's equivalent to saying that this induces an isomorphism on cohomology sheaves when you take the stalk at the unique, essentially unique geometric point of spec fq. So what is this saying concretely? Well, if you take what this is saying is that you get an isomorphism of QL vector spaces. If you take the ith on the left-hand side, what you would be seeing are the homotopy groups of bungee x with QL coefficients, And on the right-hand side, what you would be seeing are the cohomology groups, hypercohomology groups, I should say, of X. Well, I should put a bar on it. X bar with coefficients in this F BGX relative to X. Okay, so what does this buy us? Well, let's use our second description of the L function that we've associated to this situation. So this L, what did I call it? BG sub X, comma S. This is equal by invoking definition 2 to the trace, or sorry, the determinant of 1 minus q to the minus s, the Frobenius on the h star of x bar with coefficients in this sheaf, bgx over x, and then an inverse there. And if you assume this theorem, which describes what those hypercohomology groups look like, what you're seeing is the determinant of 1 minus q to the minus s phi on the homotopy groups of the moduli stack of G bundles. I should put a bar there. And then when I evaluate that at 0, what I'm just seeing is the same thing now without the q to the s factor, just the determinant of 1 minus phi on the homotopy groups of Bun GX, QL, and this is equal by the analysis that we did last time. Well, if you assume that Bun GX satisfies the Grothendieck-Lefschetz trace formula and that everything converges, this, by what we said last time, is the number of FQ points of Bun GX divided by q to the dimension of Bun GX. In other words, this is equal to the left-hand side of the mass formula version of Bayes' conjecture. So what's the upshot of this? Well, you get a proof of Bayes' conjecture. So conclusion, theorem, let me label it, theorem A implies Bayes' conjecture. Okay, so why is that progress towards proving Bayes' conjecture? What can you say about theorem A? So Bayes' conjecture is a statement about numbers, right? When you phrase it as a mass formula, you're saying you have some number on the left-hand side, some number on the right-hand side. They're defined in different ways, but they're equal as complex numbers. And this is not a theorem about numbers. It's really a theorem about vector spaces. It's vector spaces over QL. And it's a statement not that things are equal, but that some map is an isomorphism. So, and it's also a geometric statement. So note that theorem A does not reference the field FQ. It's really a statement not about, it's a statement that you could make sense of for any group scheme G over any algebraic curve over any field. And if you want to prove it, it doesn't matter what the field is. You're free to enlarge the field if you want to. So it is geometric in the sense that you can check it by replacing FQ by its algebraic closure. So it's a statement about algebraic curves over an algebraically closed field, and moreover, over the complex numbers, it reduces to something familiar. So over C, well, let's say it follows from the fact that, how should I say it, that algebraic G-bundles B-bundles on X are classified, well, it follows from, I don't know, say it like this, that Bun GX, which is something which classifies algebraic G-bundles on X, is also a classifying object for topological G-bundles on X. In other words, it follows from the fact that complex analytically, for G-bundles on a curve, G-bundles satisfy an H principle. That is, if you try to understand the moduli space of G-bundles in some complex analytic sense, it ends up being homotopy equivalent to the object that classifies G-bundles in the purely topological world, which you can actually compute topological invariants of, like homotopy and cohomology. And the difficulty is then to make sense of that H principle in algebraic geometry. Or I guess I have made sense of it by stating theorem A, but to prove that that H principle is also true in algebraic geometry. All right, how long do I have left?
4 minutes.
4 minutes. Okay, so why don't I say, so next time, I'm going to sketch some ideas that go into the proof of theorem A. There's a theorem that goes into this conclusion, but there's also a definition that goes into this conclusion. So I want to end this lecture by just saying a few words about this construction of a more basic question than how do you prove a theorem is how do you define the objects that are appearing in the statement of that theorem. So question, how to define this sheaf Fy over X in dB of X. And for example, what if Y, the main case that we're interested in is when Y is the classifying stack of a linear algebraic group, or a group scheme over X. So a related question is, how classical an object is this? So this is very closely related to an object which appears in the literature. For example, in Steinberg's work, and there's a paper of Dick Gross about the motive of an algebraic group. This is sort of a variant of that object. So let's talk about a simple case. So an easy case would be, what if G is everywhere semi-simple? It has good reduction at all points of the curve. So now this F sub y over X, it's supposed to be some object in the derived category, but when I take a cohomology sheaf of it, it's supposed to have the property that it's computing for me the homotopy groups of the classifying stack of a certain linear algebraic group. So this kind of tells you what this cohomology sheaf should look like at the generic point of X. So to describe an L-adic sheaf on X, what do you need to do? Well, first, you need to describe what it looks like at the generic point. And that should just be some finite dimensional QL vector space with an action of some large Galois group. So let's say at the generic point, what we're seeing is the ith homotopy group of, I'll call it BG eta, or what was in my second lecture was G0, the generic fiber of this group scheme. And well, you then take its classifying stack over an algebraic closure of the generic point of your curve, and then you think of it as acted on by the absolute Galois group of the function field that you're interested in studying. So this homotopy group, it's a classical object. Remember, it has another description in this case. The homotopy groups are just dual to I mod I squared, where I is the maximal ideal inside the cohomology ring of this classifying stack. So this object is classical. It's easy to describe. And I'll just conclude with a few more remarks. So you see some Galois representation that you can define concretely. And the assumption that G has good reduction everywhere guarantees that this sheaf H minus I of F is actually least. It's something you should think of as a local system. That means that this Galois representation is unramified. This representation is unramified and defines a sheaf, let's call it F sub I on X. A sheaf, L-adic sheaf in the usual abelian category of L-adic sheaves. So an idea that you might have is, at least in the good reduction case, you could try to define this object that I'm describing in the derived category, Bg sub x over x, as a sum of, well, we know what each cohomology sheaf should look like. What its minus ith cohomology sheaf should look like this sheaf Fi. And so just put that in cohomological degree minus I and add it up. And in the good reduction case, I think this is actually correct at the level of objects, that the object of the derived category you produce is a sum of its cohomology sheaves. But even though this is good at the level of objects, it's bad as a definition. Because if you try to make this your definition and then try to write down some maps that you get from functoriality, this theorem A that I stated will not be true. In order to give a definition which is functorial in a sense that makes theorem A true, you have to do something smarter than this. But since I'm out of time now, I'll just say that in order to give a good definition, you need to use some ideas of homotopy theory, which I will not elaborate on right now. Thank you.
Questions?
Yeah.
So this might be a silly question, but this sheaf you have you're trying to define here, if you wanted to satisfy theorem A, does it necessarily?
Well, there's a construction, which I didn't explain in the lecture. I mean, it's something which comes out of a construction, and theorem A is not just it's a statement about that construction. So maybe I should elaborate more on this idea. So if you were to make this your definition, you would produce something that has the same L function as the sheaf that I'm actually talking about. So it's just as good for the purpose of counting points, but it's not good for reducing questions about counting points to geometric questions about cohomology groups. This definition will not let you prove something like theorem A.
So in general, can you define, well, to expect a functional equation for L functions for like, for example, sheaves like F on the stack? Because you have an L function, you naturally expect to have a function equation, I guess, right?
Well, I mean, functional. Well, these, I mean, if functional equations for L functions are supposed to reflect some kind of duality between the L-adic sheaves that you use to produce them, I mean, I think the thing you're putting in to this construction is an L-adic sheaf that isn't really self-dual. So So, yeah, I don't know what to.
Okay, maybe in view of the time, we'll have to end there. So let's thank Jacob again.